All right, so periodic properties of the elements. Really, we start out by talking about the periodic table and part of why it's ordered the way it is and how that relates to electrons, which is what will lead us into electron configurations. So Mendeleev was the guy who put together the modern periodic table. And as you can see, he aged backwards, 1834 to 1807. Must be a typo. Yeah, and so he found this periodic law when he ordered them in terms of atomic mass. Said start with the lighter ones, go to the heavier ones, found some patterns. You got to remember at the time, they just had a collection of elements and they probably just sorted them alphabetically if they had no other way. So Mendeleev was like, there's got to be something else to these. So sometimes though, atomic mass didn't fit other properties. So he was basically trying to fit as many trends and properties as he could. And of course, Mendeleev made the periodic table, so you don't have to memorize it. But I think at least my Chem 20 students memorize at least parts of it. Because the thing is, the periodic table is great, but you need to know what all the information means. And you don't want to be spending a ton of time searching all of the elements to find tin or lead or any of the other weird ones. So Mendeleev made some predictions too about elements that he didn't have yet, based on the elements around it. Gallium, which is just below aluminum on the periodic table, not discovered by itself yet or isolated yet, called it Eka-aluminum. He predicted it would be about 68 AMU, would have a low melting point, 5.6 grams per centimeter cube density, and he was like on, or right or very close on a lot of those, which to make guesses about an element that hasn't been discovered yet, pretty good to get even one thing right. And because I think, do we have actually the periodic table that he was working on? No, okay. Because there were a lot fewer elements isolated and discovered to be their own individual elements at the time. So he was able to make some predictions. Now, his predictions, though, were just based on these trends and patterns that he saw based on the elements he did have. But he had no idea why, or he had no explanation for why those things were good predictors. So he saw a pattern, followed the pattern, he was able to make predictions, but really you can only go so far with that. And that's why knowing why is so important, because we are able to predict more accurately and beyond our patterns what could exist or what certain properties will be or what will happen if we do certain things. Actually, there's one trend on the periodic table. I'm not sure if it comes up in this class. For most elements, at least up to iron, I think it is, the ratio of protons to neutrons is close to 1. And then after you get past that, you need a lot more neutrons to add another proton. And so you get this higher ratio. So there's this magic ratio of stable elements, because I guess we haven't talked about this, right? Protons are all positively charged, so they all have positive charges, and yet somehow they're stuck together in the nucleus. Does anybody know why they're able to stick together even though they have the same charge? Huh? Nope, that's between molecules. But it's another force, and it's called the strong force. So the strong force holds neutrons and protons together. So if you've got these positively charged protons, throw some neutrons in with them, and that adds strong force to the equation, and that it allows them to bind together. So where am I going with this? The more we can know about why that's the case, why do we need this many neutrons for this many protons, there's a possibility that there are elements beyond the end of the periodic table that might be stable. Just while I'm on this tangent, right, on this periodic table, all of these elements at the bottom here are unstable. And a lot of these elements, well, actually, most of these elements, neptunium and above, all unstable, which is why they have their mass in parentheses. They're able to make these and observe them, but they exist for like picoseconds before they decay. Now, there might be elements beyond this that are heavier that are stable. We just haven't found them or haven't been able to create them yet. These get made in particle accelerators where they take heavier things and they smash just a few atoms together to try and get them to fuse. You have a question?
Yeah, what makes them stable? What makes an element stable?
Exactly. That's the why that we need to be able to answer. I don't know off the top of my head what the answer to that is. But at some point, you need too many neutrons. There's other things going on, so you can't add enough strong force for all the protons. They don't arrange in a way that's stable. And that causes that nucleus to fly apart to try and get to a more stable state. But yeah, understanding why that nucleus falls apart could tell us what we need to do to make some heavier element, which might be a superconductor, and we could have, I don't know, lossless conduction of electricity through electrical lines. Anyway, so that's why the why is important. Mendeleev created his periodic table just by sorting the masses, trying to match all these patterns. Now, actually, the periodic table is more sorted based on the electron configurations and the way the electrons are arranged around the nucleus. And we could represent those configurations of electrons with an electron configuration. Electron configurations are written like this. You've already done Alex problems with these. For hydrogen, only one electron. There's a couple different ways to do this. One is to just know the order of the orbitals and how many electrons go in them, and you just fill them in from lowest to highest energy. The other one is to use the periodic table because it tells you a lot about the electrons. So for hydrogen, we've got an orbital, and the 1 here is our principal quantum number, which you'll remember from last week. So n equals 1. S would be our L equals 0. So that's the shell and subshell. And then the superscript tells us the number of electrons in that subshell. So for hydrogen, it's really simple, but we can do one of these for every element on the periodic table. And we talked about Schrodinger's equation. So for hydrogen, at ground state, so at its lowest energy, the electron occupies that lowest energy orbital in the atom, so the 1s1. And then it turns out you can't actually solve Schrodinger's equations for multi-electron atoms exactly. So you make approximations, and you can get solutions that at least are close to experimental observations. So when we have multi-electron atoms, the reason this equation doesn't work is because there's electron spin and because of energy splitting of sublevels. So once you start packing all these electrons in next to each other, the simplest models would say that they don't interact, but they do in fact interact because they're negative charges. And so their wave functions interfere with each other to cause splitting and electron spin and these other observed properties. So we talked about the m sub s last week. In our orbital or electron configurations, we don't really take that into account. Another way to represent an electron configuration, though, is an orbital diagram. And then we're just drawing a box, or sometimes it'll be drawn as a line. Hydrogen, 1s. So same thing, you just use a line. And then this half arrow tells us what the spin is of that electron. Now for this class, whether or not your first electron in an orbital is upspin or downspin, doesn't matter. In fact, I don't know of a time where it really does matter. So if you draw it in pointing up, though, that's a positive 1/2 spin. If you draw it in going down, that would be a negative 1/2 spin. So you could draw one down. But if 2 electrons go into the same orbital, they have to have opposite spins. And so this is the Pauli exclusion principle. No 2 electrons in an atom may have the same 4 quantum numbers. So for helium, actually, I think this is on. Oh, yeah. We'll look at helium in a second. So 2 electrons in the same orbital have 3 identical quantum numbers. So it'll be the same shell, the same subshell, even the same orbital, but they'll have opposite spins. So that m sub s is different. And then this was part of the workshop last week, but so you came up with general rules for these numbers of electrons, or really the number of orbitals. So an s sublevel has 1 orbital, it can hold 2 electrons, and that means that for a p we have 3 orbitals, so we can have 6 electrons. So you always have twice as many electrons as you have orbitals, because 2 electrons per orbital. All right, so I said you can have 3 of the same quantum numbers. The 4th one has to be different, or at least 1 quantum number has to be different. So if we look at helium, which has 2 electrons, electron configuration would just be 1s2, which again, no spin information there. I mean, most of the time we don't really need the spin information. There are times where we will need it, but An orbital diagram then gives us the spin information. Again, one s orbital, so it's the same orbital, but we have one up, one down. And so for their quantum numbers, they'll both be n equals 1, L equals 0, m sub L equals 0, and then m sub S is plus 1/2 and minus 1/2. Okay, so that was 2 electrons, but we can have way more electrons depending on the element. So sublevels in each principal energy level of hydrogen all have the same energy. So if we're just looking at hydrogen, really there's just one s orbital essentially at each level. But sometimes we end up with orbitals that are the same energy. And those orbitals are called degenerate orbitals, which is not like the conventional degenerate. If you've watched Letterkenny, the degens from a... That's not what we're talking about here. It just means that instead of having their own energy levels, they're all on the same level. And so we say that those sublevels are split, or sorry, wait. The energies of the sublevels are split, not degenerate. We'll see that later. You can have sublevels splitting. Oh no, orbital splitting. Sorry, I was thinking ahead. Orbital splitting, I think we talked about in this class. That might be Chem 2. So the sublevels are different energy levels. So if we look at an S versus a P versus a D, they will have different energy levels. The orbitals within those are all, at this point, degenerate, meaning that they're all going to be the same energy level. Right, and so there's a bunch of different things that can affect these. Really, you just need to know at this point the general order of energy. So the lower the value of L within a principal level, the lower of the energy of the orbital. All in the same principal level. So it'd be saying, if we got S, P, D, and F, that'd be 4. So 4 would be lower than 4P. Yeah, 4D is lower than... Oh, no, I'm going backwards. S is the lowest, P is a little higher, D is higher, F is higher. Sometimes a lot, sometimes a little. Okay, Coulomb's law. This is one that actually you needed to know the general idea of this for one of the Alex questions last week. I think we did it on Wednesday, did one in class. So really, Coulomb's law is about the energy of attraction, or the force of attraction, really the potential energy difference between two charged particles. And for our purposes, we're going to be mostly talking about positive and negative charges. So the attractive energy, potential energy. So that has to do, or is related to the charge and the radius. All of the rest of this is constant. So larger charges mean more potential energy. Being closer means more potential energy. Because if I make R larger, then I'm dividing by a larger number, and so the energy is going to be smaller. This is important because the reason the electrons want to be near a nucleus is because the nucleus has a positive charge. So the negative charge of the electron wants to get close to the positive charge of the nucleus so they can minimize the energy, the overall energy. Nucleus attracts the electrons. The reason this is important is because of shielding and effective nuclear charge, which we barely touched on the electron configurations, but it's the second one here. We'll come back to electron configurations, actually. So each electron in the multi-electron atom experiences both the attraction of the nucleus. So I'm going to draw just a simplified atom and electrons. Remember, they're not actually like this. You could just use this to visualize. Let's just do that for now. So these are my little electrons on the outside. They want to be closer to the nucleus. But they've got other electrons that are between them and the nucleus. So these electrons in the very middle, they block some of that positive charge from the nucleus. They get in the way. And so they reduce the charge that these outer electrons feel from that central electron, or the central nucleus. You can think of it as if the nucleus was a campfire, and then the electrons are people standing around the campfire. So the electrons that are in the middle block some of that campfire heat from the people in the shell outside of them. and they'll block some from the people outside. In addition to just being farther away, they also feel less. When we're talking about the amount of attraction that any electron feels, that's called the effective nuclear charge of a particular electron. So we would pick an electron, or either pick an electron or a shell of electrons, and talk about their effective nuclear charge and how much of the attraction they can feel from the nucleus. There's the simplest way to calculate this, because I'm not sure if it's in here or if it's later, but you can calculate the Z effective simply as the number of protons of the nucleus minus the number of core electrons. If I picked let's say beryllium. So if I do beryllium and I want to calculate the effective nuclear charge of its valence electrons, then that would be beryllium's got 4 protons, and then it's got 2 core electrons. The effective nuclear charge felt by the valence electrons of beryllium would be 2. And that's a simplified calculation because the electrons, even within, I guess, if beryllium's got 2 valence electrons, those valence electrons actually interfere with each other and block some of that charge from each other. But it's a fairly small amount, and this is a pretty good approximation. All right, so there's also this concept of penetration. So the closer an electron is to the nucleus, the more attraction it experiences. And then the better an outer electron is at penetrating the electron cloud of the inner electrons, the more attraction it will have for the nucleus. And we actually saw this in last week's simulation lab, where we had, actually it's on the next slide, where you saw there were like small peaks for some of the orbitals in terms of the radial distributions, on the radial distribution functions. Actually, since I'm talking about that right now, I'll just show you right here. Right, you saw stuff like this. So like a 4s electron would have these smaller peaks inside of its largest peak. And so each of these smaller peaks is an amount of penetration that the electrons in the 4s orbital can get closer to the nucleus sometimes and slip inside those core electrons. And that decreases depending on the number of radial nodes. So like the 3D electrons or orbitals don't have very much penetration at all. They're just where they are. The 4p, though, can sometimes slip inside of the 3D, and the 4s can slip inside of the 3D also. Yeah, the 4s. But both of these, so compare these to the 4D, and these would both have higher or more penetration compared to the 4D. So we're talking about the orbitals having different energy levels. That's why the 4s is lower than the 4p, because the 4s has better penetration. So it has a higher effective nuclear charge and is more stable.
So the closer it is to the nucleus, higher penetration.
Yep. Closer is the nucleus. Yeah, the closer it can get from an outer orbital, the higher the penetrating power,
Like the 4s has
degree of penetration.
very
Yeah, there's a higher probability that it could be closer to the nucleus. Yeah. This is again just a simplified version of effective nuclear charge. So like an electron here that's on the very outside, there's 2 electrons that are inside of it. So basically 2 electrons worth of charge get shielded from the nucleus. So you'd say it only experiences about 1 plus nuclear or charge from the nucleus. Whereas a core electron inside, so if this was the 2s, the 2s would have some ability to penetrate in to get closer to the nucleus. So that allows it to get at least partly a 3 plus charge rather than being on the outside. And that's, I should say, the radial distribution functions show us how much each orbital is able to do that. So again, the 4s can slip inside. And this is saying, what's the probability of finding here? It's not, or finding the electron here, it's not 0. Some of the time, it's slipped into the inner ring of people standing around the fire. But most of the time, it's on the outside. We're not going to talk about quantitatively how that affects it. This is the total radial probability. So this is the one that makes it look like, oh, this one goes to 0 at 1. It's just not as good as this other picture. Because of penetration, because of the electron, or the different orbitals have different abilities to penetrate closer to the nucleus. That's what makes each of these sublevels, so the S, the P, the D, have different energy levels. So as to write out, and we'll see charts like this later, it's like the 4S would be lower than the 4P. So what I had on here? Yeah, 4S and 4P. And then the 4D, or sorry, the 3D would be, it actually ends up somewhere between because it's in a lower energy level, but it's higher than, because the 3D would be in the n equals 3 shell. Sorry, here we're just talking about, let's just leave it at those. So within the 4S, or within the n equals 4, S and P have different energy levels because the S has higher degree of penetration than the P. And then if we're comparing it to the n equals 3 energy level, the 3D orbital doesn't have any penetration at all. And so that's what causes it to be actually even higher in energy than the 4S. And really the takeaway here is that these different energy levels occur because of differences in effective nuclear charge. So I think to sum this up, how to sum this up? The energy of a sublevel or subshell depends on, let's just use ZEF, EFF. So the energy of a sublevel depends on effective nuclear charge. Core electrons reduce the effective nuclear charge of outer electrons. And subshells can increase effective nuclear charge through penetration. Are there any questions about that? So if we can increase the effective nuclear charge, that means that subshell is going to have lower energy. All right, basically all of that gives us these general energy levels for an individual atom with multiple electrons. 1s and 2s are expected, and it's expected that S and P would have higher energies than 1s, right? Because we've gone up in energy level. That makes sense. Now, the difference between 2s and 2p, maybe tell me why there's a difference between 2s and 2p? Higher energy difference, but it's something that we just, no? Why is this, for any atom, multi-electron atom, the 2p orbitals are going to be higher than the 2s. So just saying that they're in the n equals 2 energy level, we might assume that, or might expect that they're going to be the same energy level. This might be counterintuitive because if you've learned these already, then you're just like, oh yeah, these are supposed to be different. But really, these two are at about the same distance from the nucleus, which I think was something we saw in the simulation. Where is that? Oh, but I have. Okay, so let's do this. If I bring this up, okay, that's for the 2s. So what I'm saying is the 2s, like why is the 2s lower in energy than the 2p? Well, if you look at this radial distribution, huh? Yeah, so the 1s is blocking some of that effective nuclear charge. And so if I look at the 2s orbital, it's got some degree of penetration. Because there's this small peak in here that would actually be inside of the 1s. So what am I going to see if I pull up the p orbitals? There's no penetration. So the p orbitals don't have any ability to get past that 1s orbital to increase the effective nuclear charge. So the answer to my question would be 2s is able to, or 2s has penetration while 2p doesn't. And so the 2s then has a lower energy because it's overall closer to the nucleus than the 2p. And then it's the same when we jump up to 3s. So 3s and 3p, again, now 3s is going to have some penetration. The 3p actually at this point has some. 3d doesn't have any. So the 3d orbitals are much higher in energy than the 3p, because they'll be blocked more by all of the electrons inside of them. Okay. So again, the electrons want to be as close to the nucleus as possible. So for any atom, when we're filling in electrons, we follow the Aufbau principle, which says basically that we fill the lowest energy orbitals first before filling higher energy orbitals. So just like filling a bucket with water, it fills from the bottom to the top. Then there's our filling order, which the only weirdness in the filling order is that 3d comes after 4s. And so our d orbitals are always n minus 1 in terms of the principal shell when we fill them. You can only have 2 electrons. They've got opposite spins. And then when filling degenerate orbitals, which again, degenerate means same energy. So when filling orbitals with the same energy, we fill them singly first with parallel spins. So this is the only time where your spin really matters. And they all have to be up or down. I will always fill them down first. Or up first, sorry. Okay, so one way to think about this is a quantum hotel. Now this is a very discount hotel. It's first come, first serve. You don't get to pick your room, and you don't get to necessarily have your own room unless you're the first person, unless you don't get to have your own room. Because every room has 2 beds, and there's always 2 people per bed. Unless there's not enough people to fill the room. First floor is like our principals, our floors are our principal shell, the room is the subshell, and then the bed is the orbital. And then our people are electrons, and of course the people want to spend as little money as possible. You wouldn't go to this super discount hotel otherwise. And then 2 people per bed, and you must sleep head to foot. There's no other way to do it. I have to have opposite spins. I was going to say don't make the rules, but it literally says Dr. K's Chemistry Land. So if we were to fill this in for, let's do sulfur. And we'll do ground state sulfur. So how many electrons does sulfur have? It's on the periodic table. 16. So ground state would be same number of protons as electrons, or same number of electrons as protons. So you got 16 electrons. And so this is one way to do this, is if you know all of the orbitals and you know the order that they go in, then you just fill in electrons from lowest energy to highest energy. And so 16 electrons, I would start here. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 people come to stay at my discount hotel. First 2 people get put into the 1S room, which has 1 bed. The next 2 people get put in the 2S room, which also has 1 bed. And then next to that room, there's the 2P room, which has 3 beds. 6 people get to go in there, 2 more in the 3S, and then some people in the 3P get their own bed. And that makes sense because if you don't have to, you're not going to sleep in the same bed as a stranger, even if it is a super discount hotel, and even if you do have to sleep head to foot. So that's one way to do electron configurations. And we could write this as an electron configuration and say 1s2, 2s2, 2p6, 3s2, 3p4. So each one of these superscripts just saying how many electrons are in that subshell. It will come up sometimes, but unless stated otherwise, the electron configuration is the ground state. So if it said sulfur, I don't necessarily have to specify that it's in the ground state. You just assume no charge, so number of protons equals number of electrons. If it's not the ground state, if it is something that has a charge, So if I said sulfur 2 minus, how many electrons would that have? Yeah, so we add 2 electrons. So sulfur had 16. Sulfur 2 minus will be 18 electrons. And for positive charges, you remove electrons. Okay. Yeah, we'll talk about those. And that mostly has to do, most of the exceptions have to do actually with this part. Electrons with parallel spins have correlated motion that minimizes their mutual repulsion. Meaning to say, if you can have an orbital filled with just parallel spins, that lowers the energy. And I guess even to a greater extent, if you could have one electron in each of the orbitals in a subshell, because most of the time it happens with the d orbitals. So if this was 3d, if you can do this, then sometimes 3d will fill one electron in 4s, or I guess 3d will take one electron from the 4s. But we'll see that later. So those electrons get filled in, and in the electron configuration, we just represent them as a superscript, and we don't say which orbital they are in specifically. And you can imagine some of these get really long. So for like rubidium, every element has all of the electron configurations filled, or all the orbitals filled that the previous electron had plus one more. So we can just say the inner electron configuration of those core electrons, we can represent those with the noble gas. So if I wanted to do rubidium, which is pretty far down on the periodic table, instead of going from, oh, hydrogen's off over there, rubidium's off too. So rubidium's down here. Instead of doing all of the electron configuration for all of these electrons up to krypton, we could just say rubidium has the same electron configuration as krypton plus one more electron. And so you can take a shortcut or abbreviate your electron configurations, and rubidium could just be krypton 5s1. So just a list of these. Some more examples: lithium, beryllium, boron, carbon. And if we want to do nitrogen, be one more electron. Oxygen would be one more than that. Okay, orbital diagram for argon, and determine the number of unpaired electrons. This is maybe getting ahead of things a little bit. So argon is here. How many unpaired electrons is argon going to have? It's going to be 0. Because it's a noble gas, so all of its orbitals will be completely filled. Now, we can write those out, but we've got 18 electrons. So we have 18 electrons, so our first orbital is going to be 1s, and then 2s, then 2p. Oops. 3s, 3p. I think it might be it. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And if we didn't use up all our electrons, doing things this way, we could have written out the next orbital, start filling that one in, and you can keep going until you run out of electrons. Just like I said, there are no unpaired electrons. The other way that you can do this, do an electron configuration, if we look at, right, so hydrogen's electron is going to be 1s. If we go down to lithium, what's its last electron? What's the orbital, or the electron configuration for it going to be? It'll be 2s. This will be 2s2. This will be 3s1, 3s2, 4s1, 4s2. So these first two columns are called the s block because they all have their last electron in an s orbital, or in the s orbital at their energy level. And what about boron? Where would its last electron be? Yeah, it'd be 2p1. So we do hydrogen and helium would be, helium is over here because it's more like a noble gas, but its last electron is in an s orbital. Then it'd be 2s2, and then boron would be 2p1. And then carbon, nitrogen, oxygen, fluorine, and neon would all have their last electrons in a p orbital. And the same for all of the elements below them. So this from 13 to 18 on here, or 3a to 8a, depending on which periodic table you're looking at, that's the p block. They all have their last electron in a p orbital. And their position in the block also tells you how many electrons they'll have in their p orbitals. So boron would have 1, carbon's got 2, 3, 4, 5, 6. And then the D block's in the middle. And then the F block is the lanthanide and the actinides. So really when we look at argon on here, we say, well, it's going to be the 1s, or 1s is filled, 2s is filled, 2p is filled, 3s is filled, 3p is filled. So the position on the periodic table most of the time tells you what its electron configuration or orbital diagram is going to be. Now we start playing around with stuff outside the ground state, it changes because we just add or remove an electron. Okay. Valence electrons. For main group elements, valence electrons are those in the outermost principal energy level, the highest N level. So if it's N equals 2, then it's all the ones that have 2s, 2p. If it's N equals 3, it's going to be 3s or 3p. N equals 4 would be 4s or 4p. Those are all going to be the valence electrons. Right, this is the part that I wanted. Let's highlight this principal energy level, the highest N. Then electrons in lower energy levels are all the core electrons, and those are the ones that are shielding effective nuclear charge from those valence electrons. Does anybody know why the valence electrons are the most important for how an atom behaves? Maybe. If I take two atoms and I smash them together, yeah, the first thing that interacts are the valence electrons. So it's like this, feels weird to say, it's like the skin of the atom. I don't like that. But it's the outside, right? So if an atom bumps up into another atom, it's not the core electrons that interact, it's the valence electrons that interact. The core electrons are shielded, they're in the core. The valence electrons determine so much because it's literally the outside layer of that atom, and it's the only thing that really can interact, unless you really smash them together. So for the main group elements, so those are the ones that have the A. If you didn't know that, the A is representing the main group elements. Could also be 1, 2, 13, 14, 15, 16, 17, 18. They have the same number of valence electrons as their main group number. Boron's got 3 valence electrons, carbon's got 4, nitrogen's got 5. Makes it pretty easy. And that's really important for doing Lewis structures. Need to know those. All right, so if we do electron configuration for phosphorus. Oh, here, I'll pull up the periodic table. So we're doing it for phosphorus. So how can I tell what the valence electron configuration of phosphorus is going to be just from its place on the periodic table? We'll have 5 valence electrons because it's in the 5th main group column. But the electron configuration, what's the last part of the electron configuration going to be? It'll be 3. It's the only problem with this room. It'll be 3, and then I know it'll be P. So if I was doing it backwards, if phosphorus is over here, doing it backwards, the last part of it's going to be 3p, and then phosphorus is the 3rd element, so it's going to be 3p3. 1, 2, 3. And that means that everything before that is also going to be filled. So then the 3s will be 3s2, 2p6, 2s2, and 1s2. So what are my valence electrons and what are my core electrons? whoops, 3s2 and 3p3. So the core electrons are everything else. So this is the core and the valence. What if I did arsenic instead? So arsenic's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, what are the valence electrons in arsenic? Oh, wait, you said 4p3. That part's right. What's the highest principal shell? 4. So 4s2. Yeah. And then the core electrons? It'd be everything else, including the 3d10. It's whatever's in the highest principal shell. Like it's a little bit for arsenic because the 3d10 is filled and I have something in the 4p3 or 4p. 4p and 4s are the valence electrons. If 4p is not filled, I don't know if I really want to get into it. Because this is the way I've always taught it. This is the way my parents have taught it. But I think the newest version of the textbook actually says that these 3d is also valence electrons. But yeah, it's not in here, so I'm not ready for it yet. Oh, I guess I already explained this, but we can go over it again. So the periodic table can be divided into blocks based on the valence electrons and really the last electron and its quantum numbers, or the 4 quantum sublevels, S, P, D, and F. So group number of a main group element is equal to the number of valence electrons. The row number of a main group element is equal to the highest principal quantum number of that element. And notice how it says here, main group elements. Again, things are weird for the transition elements, which is the D block. So here's a color-coded periodic table. Makes it a little clearer. We've got in red, P block, in blue, S block, D block is yellow, F block is green. And this is where you can see some of the weird filling. Just to point out one, chromium here is 4s1, 3d5. Actually, wait. Does it go through those? Oh, yeah. We talk about the irregular configurations. I'm not going to go over this right here. But there are some weird ones like chromium, 4s1, 3d5. So instead of completely filling the 4s, we did one in the 4s, the other one in 3d. And same with over here, copper, silver, gold, rhenium, or actually technetium doesn't do that? Oh no, it's one over. Molybdenum and tungsten doesn't, but molybdenum does. So things get a little bit weird in the d orbitals. And this is again just a picture of how you can fill this. So you say the inner electron configuration, of course, most of the time you get to use shortcuts. So you just say neon. And then the rest of it for chlorine is all of the orbitals that come before it. So since it's past the 3s block, it's 3s2, it's the 5th element in the 3p block. So then it's 3p5. Faster than writing them all out. All right, so the electron configuration for bismuth. Oh, fun. So bismuth, all the way down here. So let's do this. We're going to use the shortcut. Xenon is the closest noble gas before bismuth. So basically you go up a row into the end. So I can say, okay, all of my core electrons can be represented by xenon, and I put that in brackets. Now, which other blocks are filled before bismuth? S and D, so 6s2, and then what would the D block be? It's 5d, 10. There's one that you missed. Where do these go? The lanthanides. Yeah. So the lanthanides actually go in here after lanthanum, and the actinides go after, was it actinium or actinide? Lanthanum and actinum. That doesn't feel right, but I don't say it very often. Just like the 5D is 1, right, we subtract 1 from the row number. Similarly, for the F block, we subtract 2. So this becomes 4F, and then how many electrons to fill the F block? 14. So 4F, 14, and then 6P, 3. And then you can always double check, because for the ground state, I should have the same number of electrons as I have protons. So bismuth should have 83 protons, or sorry, 83 electrons. So I took a shortcut, but xenon, all of its electrons should be 54. So this xenon here represents 54 electrons. And then if I add 2 and 10 and 14 and 3, 26, 29, so those are all 29, plus 54 equals 83. So if we had left out the or the F block, the F orbitals, we'd be short by 14 electrons. So you can do that to just check. And then make sure if you're doing something not on the ground state, so if this had been bismuth 1 plus or bismuth 3 minus, then you take that into account in your total number of electrons. Any questions about electron configurations? Okay. Do you have time to get into something else? Oh, irregular ones too. Sure. I guess I'll write these in just quickly. Oops. So chlorine in the third row should be 3s2, 3p5. Silicon would also do neon, and then 3s2, 3p2. Strontium would be krypton, and then 5s2. Oxygen would be, it's almost not worth doing, but helium, 2s2, 2p4. And I did all of those just from where they are on the periodic table. And again, if you don't trust yourself that much, you can go back and check and just add up when you use a noble gas. So krypton, how many electrons would that be? Krypton's over here, 36. So if I had 36 to 2, I should have 38. Okay. There are some irregular electron configurations. So again, because sublevel splitting, which is just, I guess, the phenomenon that sublevels in the same principal shell have different energy levels, rather than all having the same energy level. The 4s sublevel is lower in energy than the 3d, which is why we fill in 4s before the 3d. But they're really close in energy. So where that last electron goes depends on, or I guess where the electrons go depends on some other factors. And mostly, this is when we have either a complete or a half-filled or a completely filled d orbital. There's a little bit of extra stability that comes from either half-filling or completely filling that orbital, and so that, or that subshell, so that changes where that last electron goes. And these are found experimentally. Somebody does the science. I actually don't know what that experiment looks like. So these are the weird ones, irregular configurations. I'm not expecting you to memorize these because I think it makes enough sense. I would not give you something like ruthenium, where it's 5s147, but I might give you chromium, where it's 4s1 3d5. And I'll have you write out an orbital diagram. So if we wrote out the orbital diagram for this, we'd get 4s and then 1, 2, 3, 4, 5. That'd be the 3D. And so when you fill this in, if we filled it in normally, it would go 1, 2, 3, 4, 5, 6, and you fill it in that. And what I would expect for you to be able to see is that, oh, this is, or could be half filled if I took one of these electrons and put it over there. And so you would erase this one from the 4s and put it over here so that you can have a half-filled 3D. Or like copper. You would do 4s. You do 1, 2, 3, 4, 5, 3D. You say 1, 2, 3, 4, 5, 6, 7. Normal filling would be this. But you say, oh, I can move this electron over here, and that would completely fill. So I do expect you to be able to see these ones for the half filled and completely filled, not for, and when it's one away. So like ruthenium, where it's, I don't know why this, actually, I could take a guess at why it does this, but we haven't covered it, and I don't think we do. Or palladium, where they all go into the d orbital instead of the s orbital. Those ones are a little weirder, but like copper or chromium or molybdenum. So it's just these completed sets. And I guess I think of these, the analogy in my mind for these is that they're like collectors. So if you've ever collected something, you want to have the complete set. Actually, when we were at the Naruto theme park in Japan, we bought all of the, you had to buy the drink along with the bottle. So there was Sasuke, Sakura, Naruto, and Kakashi. And my wife needed to have all of them, not just some of them. She needed the complete set. So electrons are like that too. They'd rather have either the half-filled 3D or the completely filled 3D set than just a filled 4s. I don't know. Maybe it helps, maybe it doesn't. Yeah, because this is getting into the quantum mechanical model explains. So this explains the way that these orbitals fills explains a lot of things. Because these valence electrons, the way that they fill is periodic. That's why once a valence shell is, or once the valence electron orbitals are filled, it moves to another row. And because every time that those fill, we get a repeat in all of these properties because of the number of valence electrons. So on Wednesday, that's what we'll go over. And again, these are the most important topics that we covered today for this chapter. The other ones are things that you should be able to, once we've talked about it once, you should be able to derive it from these first principles. Okay, so we'll do that on